All right, we have here an integral today from MIT 2022, number 15, and there's definitely quite a few ways to do it. You could split it into two integrals, but I don't think I want to do that. I have kind of an unusual way. It's similar to like integration by parts reverse product rule. It's just recognizing if we have something in the form like this with tan and secant with different exponents, when you differentiate this, you're going to get something similar to this right here. It's not always going to work, but we're looking at an integration beast, so they probably set it up for us pretty nice. So what we can do is take a derivative of this and just see how it lines up. You also could remember a formula, but I always forget that formula. So let's differentiate using product rule. So first we'll have power rule on this first part. So we'll have tan n minus 1 x. Then chain rule on this is going to be secant squared x, and then we just bring this part along. Then for the second part of product rule, we're going to keep this right here, then differentiate this first with power rule, the m, bring it all the way up front, secant m minus 1, then chain rule on this is just going to be secant x, I don't know if I have space, tan x dx. But then we can just clean it up, combine like terms. So then here we can combine the secants. And then over here we can combine tangents and secant. So this is going to become tan of n plus 1. And here, multiplying secant times this with the minus 1, basically you can cancel that with this, and we're just left with secant mx. But now at this point we're in pretty good shape. You might notice the pattern here, like, okay, if the difference between m and m plus 2, the exponent on m, it's differing by 2. That matches our problem here. We're going from 3 to 5, differs by 2. Over here, same kind of thing on tangent. Going this way, differs by 2, from n minus 1 to n plus 1. That works like this right here. So to set it up how this is going to work, if m is 3, that's going to match that there. So then n plus 2 is 5. And then on n, we want n equal to 3 as well, because then here we get a 4 right there. And then here, this is going to be a 2. So let me get rid of our in-between line here, because it doesn't do anything for us. And then we know our m and n, so we can just kind of plug it in right here and set that up. And then let me just rewrite the du line, plugging back in the m and n value so we have actual numbers on it, plugging in also on the coefficients here. And what just happened, the du is almost exactly this. The only difference is there's this coefficient of 3. That's going to be really easy to fix because constants with derivatives just kind of can be pulled out front and factored. So, and maybe another way to look at it, if you want, just factor the 3 out and write it like this. And so if we multiply by 1/3 right here, the 1/3 is going to come along and just cancel that. Now there's really no reason to actually use du and be formal about it. It's just notation, because we're just saying that this is going to be the antiderivative of this. So, but doing the substitution out if you want, we're saying our whole integral is du. So when we integrate it, we get u, and we just plug in this for our final solution on it. It's just going to be tan cubed x, secant cubed x, all over 3, add a plus c, and that's it. So like I said, it goes pretty quick. It goes quicker if you use the formula because it's always got that pattern of differing the exponent by 2. These do come up once in a while on the integration bees, so you can kind of go right to this kind of setup and like almost just kind of start plugging in exponents. Like I said before, it's basically the same thing as reverse product rule, just kind of saving some time knowing right away that it's going to be in this format right here. Okay, there you go. That's it for today. Thanks everyone for watching. Have a good day.